So, in this session, just after finishing the laminar flow, just we are going to discuss this turbulent flow in pipes. So, the outline of my today's presentation, the first we discuss the introduction, then the friction losses, because in all the time we are calculating the major and minor losses. So, how we calculate this friction head? So, this equation is very important equation known as the Darcy-Weisbach equation. So, today we derive the Darcy-Weisbach equation. Then the shear stress in the turbulent flow. So many models, yes, how you calculate, like viscous flow, the Newton's law of viscosity tau equal to mu du upon dy. Like similar way, we discuss what is the shear stress in the turbulent flow. Then the velocity distribution. So, what is the universal velocity distribution for the smooth, velocity distribution for the smooth and for the rough pipes. So, in turbulent flow, if fluid motion is irregular, yes, if you know in the first in the kinematics we discuss what is the laminar and turbulent flow. We can say on the if there is a zigzag like a flood water in the turbulent flow. Laminar flow is the across stream line across, but this movement is the straight line, but in case of the turbulent flow the motion is the irregular. So, there is the complete mixing fluid. Why this is the complete mixing? Due to collision of the fluid masses with one another. So, fundamentally on the basis of Reynolds number we can categorize the fluid nature of the fluid, laminar or turbulent. It is seen that the up to 2000 or 2300 the flow is the laminar, when I am talking about the fluid flow in the pipes. On the other hand, up to 2300 or 2000 up to 4000 is the state, is the some transition state. We cannot say, sometime it behave like laminar, sometime it behave like a turbulent. So, in the laminar flow we have in detailed discussion in the laminar flow what is the velocity distribution. The velocity distribution is the parabolic in nature. At the center velocity is the maximum, at the initial is the boundary it is the 0. We have derived u equal to u max 1 minus r upon r capital R square. We have derived u average equal to u max upon 2. So, all the time we have solved some numerical by these fundamental equations. So, if you see, we take the example of the fluid flow through the pipes. If you see the velocity distribution for the laminar, if you say the laminar, if nature is the laminar, this one is the is the boundary maximum parabola. So, u maximum, nature is the parabolic. So, this one is the velocity distribution of laminar. What about the turbulent? What is the turbulent? Nature is the different. Nature is the logarithmic logarithmic. It depend upon power law, y upon delta 1 power 7th power 1 upon 7th power law. Some with the flatter. If you see, not like this, some flatter, some flatter, and so this one is the turbulent. Just see, this one is the turbulent. This velocity die, this one is the turbulent. Velocity, this power law, depend power law, are logarithmic. logarithmic. So, this is all about the velocity distribution of the laminar and turbulent flow. Yes, turbulent flow means zigzag. Yes, all the mixing. Yes, mixing. Yes, most of the flow is the, yes, very few example is the laminar, most of the flow is the, yes, in the real practice the turbulent flow. So, on the basis of Reynolds number, Reynolds already decide inertia force upon viscous force, and this Reynolds number is the rho a v squared, yes, or rho a v upon mu. This not like this, rho v d upon mu, this one is the Reynolds number. So, if Reynolds number is the less than, if you see Reynolds number, if Reynolds is the less than 200, so this one is the laminar, otherwise yes, in between yes 4000 2000 to in between, so this become transition state. We can't say. If it talks about the motion, turbulent motion, so what at the wall turbulence, at the wall level, at the free turbulence, yes, at the free turbulence, yes, when the mixing takes place, where the convection, yes, sometime the where the actually conversion takes place, potential is the changing in the kinetic energy. So, these are the some at the wall level, at the free turbulence, at the convective turbulence. So, if fluid flow through the pipes, it is seen that the, yes, the frictional resistance, yes, if fluid flow, the frictional resistance are there, and it is seen that the it is proportional to V power n. And what is the n? Because n is the n depend upon this value of n depend upon the this one the surface material. So, in case of the turbulent, because it vary from 1.5 to 2, the coefficient V n, yes, vary. If you see this HF, yes, frictional resistance is the V power n, but in case of the turbulent flow, it is not twice V power 2 in case of the turbulent flow. Okay. Then it depend upon the proportional to the surface area, but it independent of the pressure and depend upon the contact surface nature, contact on surface nature. So, propelling force on the flowing fluid between two sections. If we see we have taken the section, this one two section 1 1 1 1 and 2. The pressure acting is the, yes, control volume pressure acting is the P1 at the P2. What is the propelling force? P1 minus, yes, pressure difference into area. This is the propelling force. P1 minus P2 into A. Propelling force, what is the this P1 pressure into area, this one is the force, and what is this propelling force? Propelling force of, what is the propelling force of flowing fluid between two sections, P1 minus P2 into A, area of cross section. What is this? This one is the valence, this propelling force is the valence by the resistance force, and the resistance force, yes, from where it comes? By the friction, and this equal to F dash, because this F dash, so many, yes, dependent, this one the non-dimensional term, we are assuming any F dash which depend upon the nature and material, yes, of the pipe. Then P, because this resistance force dependent on the P. What is the P? Weighted perimeter, this P, yes, P. So, this resistance force, yes, resistance force is proportional, yes, or this equal, we can say this equal. So, this resistance force is equal to V R, yes, F dash P, weighted perimeter, capital P, weighted perimeter. Weighted perimeter, weighted perimeter P, then length a pipe V, turbulent, in case of the turbulent flow, this is the V square. So, any, what is the F dash? F dash is the, yes, without dimension, without dimension. So, this force P 1, one force is the P 1 minus P 2 into A, and this one is the valence, yes, by. So, under equilibrium F dash P L V square, this one is the very fundamental, we can say this is the equation 1. In equation 1, because this one is the propelling force, and this force, what is this force? This one is the resistance force, So, by divide both side by W. What is the W or gamma W? Is specific weight rho into G. This is the W. We can divide, no problem. So, that is why we are writing this P 1 minus P 2. This equation is the similar. Yes, can we move forward? This one is the very fundamental. So, we are going to forward. Yes. So, if you see before this P 1 minus P 2 upon W into A equal to F dash L P L V square upon W. Again we can write, what is this? We can R P 1 minus P 2 upon W equal to F dash W P upon A, area, this area, P upon A L V square. And what is this? This is the HF, head loss. This one is the head loss, HF, P upon W, head loss. So, the head loss F W, P upon A. So, we can write this term HF, we can see, just see HF. Okay. We can, yes, by this equation we can write HF. We are going to multiply because by 2G, divide and multiply 2G up and down, Why like this? Because V square upon, if you know Bernoulli equation, velocity head V square upon 2G is the form of the velocity head. So, multiplying, yes, divide by 2G, numerator upon, no problem. So, we can write this one HF equal to 2G F dash upon W P upon A, yes, L V square upon 2G. So, this one is a very simple. So, that is why at HF 2G F dash upon W L, okay, V square upon into L. And what is this component is the very important. What is this? Weighted perimeter upon area, weighted perimeter upon area. So, one is the, we are defining the M, hydraulic mean depth. So, A upon P, and what is A? Pi by 4 d square, and what is the weighted perimeter? Pi into d. This pi cancel, d. Oh, yes. So, this become d by 4, means hydraulic mean depth m equal to area upon weighted perimeter. This one is the area upon weighted perimeter. So, this value m. So, we can write if P upon A, because A upon P become m, and reverse of that P upon A become 1 upon m. So, we can write L upon m, because so we can write 1 upon m. So, L upon m, that is why this is like this equation L upon m, because L and 1 upon m become L upon m, okay, and all the equation remain same. So, HF equal to 2g F bar W L upon m V square upon 2g, V square upon 2g. This one is the, if you see, this one is the, what is the L? Length of pipe, m hydraulic mean depth. This component is the, yes, we are separating. All these are the, if you see this component, if you see this all dimension of this, if you see dimension of this component is the similar, is the dimension is this HF. What does it mean? This component, total component, and what is this total component? 2g F dash upon small w is the dimensionless, because this dimension is equal to HF dimension. So, this value, this one is the, this quantity, and what is the quantity? 2g F dash upon w is dimensionless, okay. So, if it is dimensionless, then HF equal to, we are replacing another constant, we are replacing it by another constant. Okay. So, what is this? This become HF become F, another constant F, L upon m V square upon 2g, simple. And what is m? Yes, m equal to, what is this? A upon P, and what is area? Pi by 4 area, d square, weighted perimeter, pi into d, d cancelled, pi cancelled. So, this become d by 4. So, m, in place of m we can write d by 4, in place of m we are writing d by 4, this. So, F L d by 4 V square upon 2g. So, yes, numerator 4 F L V square into d into 2g. So, this become, so this equation, what is this? H F equal to 4 F L V square upon d into 2g. This is known as Darcy-Weisbach equation. This equation is known as Darcy-Weisbach equation. And where? What is F? F is the coefficient of a friction. This F, at this equation, the F is known as coefficient of friction. Coefficient of friction. So, sometime some numerical problem, this coefficient of a friction is replaced by friction factor. Yes, if this 4 F is replaced by F dash, yeah, any F. So, this F become friction factor. So, sometime in place of 4 F we are writing F, F L V square d into 2g. So, this F become friction factor, this is the friction factor. So, what does it mean? This F1 or F dash equal to 4 F, and if this F is the friction factor and another F is the coefficient, another F is the. So, if there is the 4 F equation, so we put, so there is the confusion, if 4 F means friction factor, if only F is the friction factor. Okay. 4f friction coefficient, f where only f is the friction factor. So, this one is the yes Darcy-Weisbach equation. By this equation we use for the calculating major losses in fluid flow through the pipes. When fluid is flowing through pipe, there are so many losses occurs. So, this major loss is the due to friction, and the due to friction major loss is calculated by the Darcy-Weisbach equation, and this equation is the HF equal to 4 F L V square upon D into 2G. So, the next again the coefficient of friction in the term of the shear stress. Sometime what is the coefficient of the friction, very fundamental. Yes, the you know the shear stress, the propelling force, this P1, you know the P1 minus P2 by A is the valence by the shear stress. Yes, yes, in term of the shear stress at the boundary level, shear stress is the shear stress. What is the surface area? Pi dl, and this area is the pi by 4 d square. Yes, so P1 minus P2 pi by 4 into d square into pi dl, okay, pi dl. So, this we can calculate by this. What is this? D cancelled out, pi cancelled out. So, we can write P1 minus P2 equal to 4 times tau naught into L upon D into L upon D. So, by this equation is the derived by this. Second is the what this by the friction loss. Yes, HF by this, you know the HF. What is the HF? HF is the P1 minus P2 upon W. This is the HF, rho into G. Okay. And what is this? 4FL, 4FL V square D into 2G. So, we can W. So, this become P1 minus P2, both we are equating both equation, and if you are equating both equation, what are both equation? 4 tau naught L upon D equal to 4 F L V square 2G into D into W. We can write what is the W? Rho into G. So, just see L cancelled out, diameter cancelled out, okay. This cancelled out. We can write what is the friction factor? This 4, what is the friction factor? Friction factor equal to, so this G cancelled out, we can write twice only, yes, only 2 twice shear stress this value upon this rho into V square, rho into V square. What is F? This F, what is this? F is the coefficient of friction. Coefficient of the friction. So, this one is the friction head loss of, okay. Next is the shear stress in the turbulent flow. How you calculate the shear stress in the turbulent flow? In order to determine the magnitude of the turbulent shear stress, a number of semi empirical theoretical models have been developed. The first model is the Bosanquet theory, where the total turbulent, if you see the total turbulent T, yes, equal to viscous and turbulent. And what is the turbulent? This turbulent is neta, yes, eddy viscosity. This one the temporal velocity upon dy. So, the turbulent, this shear stress, turbulent shear stress sigma b is the viscous shear stress, okay. So, the total shear stress is this one is the total, not this is the total, this is the total, total. So, viscous plus turbulent, and viscous is the Newton's law of viscosity mu du upon dy plus neta upon dy. Another is the Reynolds theory. Reynolds theory. If the amount of mass of water or liquid is the fluctuating to adjacent layer. So, there the fluctuating velocity is the u dash v dash. Then we can say the shear stress tau, we can shear stress tau, yes, we can write shear stress tau rho mu bar v. This is the shear stress tau, and this shear stress, this is the fluctuating component. This one is the fluctuating components. So, by temporal we can take mean, we can write like this mu dash, or we can we can easily write u dash. This one is the Reynolds theory. Then the Prandtl mixing length theory. We know the Reynolds theory means the Prandtl mixing, in the lateral some liquid mass of the few mass of the liquid is the mixing with the at the lateral length, okay, the lateral part. If the lateral part, so we can calculate what are the components. Components is the u dash L, the particular length. So, we can the fluctuating component u dash equal to L du upon dy. And what about v dash? Similar, same L component, lateral, some mass is the before gaining the new velocity it the mixing, the lateral length is the mixing. So, if we multiply, so this component L square du, if you have, because we know the Reynolds shear stress. What is the Reynolds shear stress? This one is the Reynolds shear stress, rho, this is the. So, if you are multiplying, so this become this component, if you are multiplying rho multiplying this component. So, what is the total shear stress? The total is the, we are adding the viscosity, this component, viscous component, and this component is the this component. Okay. So, the total is the, we can say like this, If you see the velocity universal velocity distribution. So, this one is the Prandtl, you know the L equal to this value, this was the Karman constant. So, shear stress again squaring at the boundary level, shear becomes shear naught. So, putting the tau naught equal to calculating du upon dy. So, this become du upon this term, and what is this? So, this become this uf, and what is the uf? Uf equal to shear stress upon rho shear friction, this friction. So, if we calculate by boundary condition, these are the boundary condition, we find the C, putting the boundary condition value, the real equation, and we get this one is equation. This is the called, this equation is the called Prandtl universal Prandtl universal. Similar, if we calculate in the smooth pipe, smooth, and this one is for the rough pipe. Okay, thank you.